All right, calculus, we are looking at FRQ trend number 3 with differential equations. Okay, so what's going on with this? First, you're going to be given a differential equation. And that looks something like dy dx equals something, or dr dt equals something, or dv dw. It doesn't really matter what they are. This is probably your most common one, dy dx, but that's what you're going to be given. And then you're going to be asked to do two things. One, you're going to have to find the original function, original equation. Not the differential equation, but the original one. And along with that, you're going to have to be doing a lot of interpretation. And this interpretation comes from looking at, increasing, decreasing, a positive, negative, those kind of things, and even a little bit of concavity and how to compare all those things in there. And some details that go along with it, if you're going to be finding the original equation, they're going to give you, you're going to also be given a particular value to solve for C. So you can solve for C, that constant of integration. Well, let's jump right in. Here we go. Here we go. Differential equations. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. Increasing function, alright, so they already told us W, models the total amount of solid waste stored in the landfill. Planners estimate W will satisfy the differential equation dW dt equals this for the next 20 years. Alright, so now I'm looking at T is going from 0 to 20. Alright, that's interesting. W is measured in tons. T is measured in years from the start of 2010. Okay. Use a line tangent to graph at W to approximate the amount of solid waste. Alright, so some buzzwords that stand out in this. First, approximate, and second, tangent. That means that I'm going to have this equation, y minus y1 equals the slope times x minus x1. And another way of thinking that is y minus f of x1 equals f prime of x1 times x minus x1. And then you can go even further here. You would move this thing over. Then y equals f prime of the specific x1 times x minus x1 plus f of x1. All right. At time equals 0. 0. Notice that. So do we know something about 0? Do we know what w of 0 is? Actually, we do. It was given to you, if you look back in here, I'll highlight it in the prompt, but it was given to us right at the beginning. At time equals 0, w equals 1,400. And dw dt, you would just plug that in here. Okay, so let's see what we would get there then. So I'm using the letter F here, but this is really w. So w prime of 0 times x minus 0 plus w of 0. Well, w of 0 equals 1,400. W prime of 0 is going to be 1 over 25. If we look at what that equation was, it was 1 over 25 times 1,400 minus 300. So we got that piece and this here. We just got to fill in this x, or this t, I guess you could say. So that's kind of interesting. I used x's all over the place, but it should have been a t. This should be a t. This is our final piece here. The first three were just kind of scratch work to build up to that. So t, and this is 1/4. That's what they're talking about here. 3 months, because each unit is a year, so 3 months would be 3 out of 12 months, so t equals 1/4. So y approximately equals w prime of 0, which we calculated over there, times 1/4. Whoops. I don't know where this equals came from. Times 1/4, because 1/4 minus 0 is 1/4, plus w of 0. And we have already labeled these from up here. Boom. That was it. Next. Find d squared w in terms of w. D squared w to determine whether your answer in part A is an underestimate or an overestimate. Okay, so let's talk about under versus over when we're doing approximation. So if the line is tangent like this or this, but we are concave down, the line is going to be over because it's on top. But if we are, this is concave down. But if we have our tangent line, no matter if it's increasing or decreasing, and it's concave up, it's going to sit like that. So then it's under. So all we got to do is figure out if we're concave up or concave down with the second derivative at t equals 1/4. Okay, so dw dt equals 1/25 times w minus 300. And if I were to simplify that a little bit, that'd be w over 25 minus, what's 300 divided by 25? That's 12. But honestly, who cares? Because when I take this next derivative with respect to t, I'm going to have, what's the derivative of w with respect to t? It's dw dt times this constant, which is 1/25. You might be asking yourself, well, wait a second, is that positive or negative at w equals 300? Well, dw dt, this piece, is plugged in right there. So this is really 1 over 25 times w minus 300 times 1 over 25. Oh, no, wait. So the question then is, at t equals 4, trying to check it at near, I should say near, t equals 0. And we said that w is actually 1400 at t equals 0. So this would be 1/25 times 1400 times minus 300 times 1/25. And we don't really care what that equals, but we do care that it's greater than 0. It's positive. So d squared w dt, this should be dt squared, is greater than 0 when t equals 0. Therefore, the approximation is what? Okay, so we are greater than 0. That means we're positive. That means we're concave up. That means we're underestimate. The approximation is an underestimate. Booyah. Next. Find the particular solution w equals wt with a differential equation with initial condition w0 equals 1400. Hey, figure that out. Look, they gave it to us right there. All right, so first things first. One, separate. What do we got to separate? W's and T's. So I got to move this term right here, w minus 300, down to the bottom over there, and this dt up to the top over there. That's going to give me dw over w minus 300 equals 1 over 25 times dt. At this point, you're probably asking yourself, how do I do this? Because I need to integrate both sides. I need to integrate both the left and the right. And down here, I got like a u substitution. Let's say u equals w minus 300. Then du dw is just 1, or du equals dw. So I can do, this is the same thing as the integral of du over u. Well, the antiderivative of that is natural log of u, absolute value, of course, equals, now on the other side I'm going to have 125 times t plus a constant c. And then we kind of go through this big old thing, and you start to get down to the point where you say, u, which was really w minus 300. W minus 300 equals c e to the 1 over 25 t. Alright, so when t equals 0, w equals 1400. So 1400 minus 300 equals c times e to the 0, which is really just c. So 1400 minus 300 equals c. So what's the function then? That means that w of t equals, the c is going to be 1400 minus 300, that's 1100, times e to the 125 t. Check done. Answer finished. It's really helpful in this context to kind of memorize that when you have natural log of y equals e to the x plus c, that's going to become y equals c e to the x. These are kind of interchangeable here. It has to do with just trying to, oh no, I shouldn't say it like that. X plus e, pardon me. Here we go. X plus c. And you bring e into it both sides and you get this down here. Okay, do we have anything more from this problem? No, that's it. That's the big idea though, and that's kind of what was summarized there. So let's add an empty page. Let's move on. The rate at which a baby bird gains weight, that's interesting, more W. And its current weight at t equals 0 when the bird is first weighs, its weight is, okay, so b of 0 equals 20. Alright. Let y equals b of t, the solution to the differential equation, b of 0. Oh, they gave that to us there. And here's our differential. Is the bird gaining weight faster? Gaining weight faster. That means, is the rate more? That's what faster means. Is the rate more at w, or at b, I guess you could say, equals 40? Or b equals 70? That's the question. So let's answer it. So when b equals 40, db dt is going to be, let's double check this real quick, 1/5 100 minus b. 1/5 100 minus 40. At b equals 40. And then db dt at b equals 70 is 1/5 times 100 minus 70. Aha! Now check this out. This calculation over here on the left, if I subtract 40, that's 60. 60 divided by 5 is what, 12? And over here I got 30 divided by 12, that's 6. This is greater. So db dt is greater when the bird weighs how much? Bird weighs 40 grams. Therefore, it's gaining, the bird is gaining weight faster at the time. Faster at that time. Done. Alright, let's see another one. Okay, find d squared b dd squared in terms of b. Use d squared b dd squared to explain why the graph of b cannot resemble. So this is a proposal for b, but it's wrong. It's not b. This is not b. And the question is why? Well, we got to figure out the derivative. So if db dt equals 1/5 times 100 minus b, yeah, let's simplify that. That's going to be 20 minus 1/5 b. Then d squared b over dt squared is going to be 0 minus 1/5 db dt, and really this piece right here is going to get plugged in there, so that's going to become negative 1/5 times 1/5, alright, times 100 minus b. So here's something that's kind of interesting. I don't know if you see this, but check this out. When b equals 20, the initial weight, then d squared b over dt squared equals negative 1/5 times 1/5 times 100 minus 20, which is not really a big deal to figure out what that is, except that it's less than 0. Less than 0, which means that B is concave down at t equals 0. Which is not true here. Check this out. This is concave up. And it's not. It's almost like these should be flipped, if anything. And in fact, there's a lot of other things you could use to disprove. But the concavity is basically kind of what I'm looking at. So cool. That was easy to prove. Easier than I've done it before. So use the separation of variables to find y equals b of t, the particular solution to the differential equation with its initial value b of 0 equals 20. Okay, so we got db dt equals 1/5 times 100 minus b. Well, let's go a little bit with this. We're going to take this piece here, and it's going to go down. We're going to take this piece here, and it's going to go up. That's called, algebra. So we would have db over 100 minus b equals 1/5 dt. Now that we're there, we could take the integral of each side. This one on the left is going to require a little bit of substitution. If u equals 100 minus b, then du db is going to be -1. So we've got to put a -1 in there, put the db over here to balance things out. So this would be the integral of -1 times du over u, which is going to be -1 times natural log of the absolute value of u being 100 minus b. So back to this, that means I'm going to have -1 times natural log of, what do we got here? Natural log of 100 minus b. There we go, 100 minus b. Equals, on the other side, 1/5 t, and of course we need a constant in here somewhere. So let's multiply both sides by -1. Now I'll get rid of that negative. Then I'm going to take the e of each side, and that's going to give me 100 minus b equals e to the -1/5 plus c, which if I keep going with this, I'm going to drop that c down, and I'll have 100 minus b equals c times e to the negative, this should be a t right there, -1/5 t. Now we know that b of 0 equals 20. So when we plug in 0 for t, this should be 20. So that means 100 minus 20 equals c times e to the 0, which is really just c. So 80 equals c. How are we going to figure this out now? That means that 100 minus b equals 80 times e to the -1/5 t. We want to get this b all by itself. So I'm going to move this over there and this over here. So that'll give me 100 minus 80 e to the -1/5 t equals b of t. Ah, that was long. About to lose my breath on that one. Lots of algebra, but pretty straightforward, pretty standard, similar to the last one. Hopefully you're noticing a trend. Yeah, hopefully. Alright, differential equation. They are going to do it to us now. Now they're going to give us a slope field. Not that big a deal, but still a possibility with differential equations. So let's take a look at what's happening here. dy dx equals x plus 1 over y. So I'm going to make, for myself, a table. And notice here that I have to go from -1 out to 1, and from -2 up to 2, and I'm skipping across the middle. So I'm going to have -1, 0, 1, and then 2, -1, skip the middle. Now I'll go down to, whoops, that's +1. This is -1, that's +2, and this is -2. So I'm going to have kind of like a little table here. Let's calculate this stuff. Calculus, we're going to calculate. In the middle, we're not doing it. So x plus 1, so add 1 to x, then divide that by y. Add 1 to x, add 1 to negative 1, and you got 0. 0 divided by anything is 0. So that's 0, that's 0, that's 0, that's 0. That was easy. Add 1 to 0, so that gives us 1, so this is 1/2. This is 1 over 1. This is 1 over negative 1, and 1 over negative 2. Okay, these aren't too hard. Then we add 1 to 1, and that gives us 2. So that's 2 over 2, 2 over 1, 2 over negative 1, and 2 over negative 2. Alright, so all this put together gives us some slopes. That means we got slope 0 here, here. And then now we have 1/2, which is kind of a shallow slope. Then 1, which is like right at 45 degrees. And then negative 1, that's negative 45 degrees. And negative 1/2, that's kind of shallow again, like this. Then we got 1 here. And a negative 1 here. But then we're steeper on these ones. So that looks like what we're going for. Now the question is, while the slope field in part A is drawn only at 12 points, it is defined at every point in the xy plane at which y does not equal 0. Describe all points in the xy plane y does not equal 0 when dy dx equals negative 1. Oh, we also got to sketch a solution curve, so let's do that. That means that it goes through 0, negative 1, so down here. So there's our curve. And it looks like once we get over here, we start to flatten out. There we go. So that looks like that curve. This means when is the slope negative 1? Well, for the slope to be negative 1, that means that the ratio of the top, that means that the top x plus 1 divided by y equals negative 1. Whoops, not negative y, negative 1. So now that we get into that, you know what, I just kind of answered this first one there, but now I got to get to this one. So this means that dy dx equals negative 1, which is x plus 1 over y. So what I got to do now is kind of get this y up here and talk about it in terms of like an equation. Negative y equals x plus 1. If I were to multiply both sides by negative 1, I get y equals negative x minus 1. There we go. That's it. Because it says describe all points. And that's kind of like an equation. Whenever that's kind of an old school way of doing an equation. It says all points that work for something is just give it an equation. Okay, find the particular solution y equals f of x to the given differential equation if this. Okay, so now what we have going on. At this point, we know that dy dx equals x plus 1 over y. We got to separate, move the y's with the dy's, x's with the dx's. We're going to have y dy equals x plus 1 dx. And we got to integrate. This is super easy compared to the other ones. It's just y squared over 2 on this side. And on the other side, we're going to have, this is x to the first, so it's x squared over 2 plus x. And we've got to put a plus c somewhere here. Now this says f of 0 equals negative 2. That means x equals 0, y equals negative 2. So we're going to have negative 2 squared divided by 2 equals 0 plus 0 plus c. Well, what does that come out to be then? Negative 2 squared is 4 divided by 2 is 2, so 2 equals c. So taking this and directly translating it, that means that y squared over 2 equals x squared over 2 plus x plus 2. Now the question is, do we have to do anything more? Yes, we do have to get y by itself as a function of x. So we multiply both sides by 2. Get rid of this 2, and we got y squared equals x squared plus 2x plus 4. And what do we got going on next? Well, from here, then we got to take a square root. So f of x equals square root x squared plus 2x plus 4. Now it's done. Wasn't too hard. That was pretty straightforward there, but kind of different. When you're dealing with slope fields, it's a little bit different. But we were consistent in the fact that it was still asking us to find an original equation given the differential. Let's look at the next one. Solutions to the differential equation also satisfy this. Let y equals f of x be a particular solution with f of 1 equals 2. Write an equation for the line tangent to the graph at x equals 1. Okay, so let's just jump right in there. Line tangent x equals 1, that's like saying y minus f of a equals f prime of a times x minus a, and a equals 1. So that means y minus f of 1 equals f prime of 1 times x minus 1. Well, f of 1, do we even know what that is? Yeah, we do. They told us here a second ago, f of 1 equals 2. And there's my derivative there. So f of 1 equals 2. And f prime of 1 is going to be, this is my x, this is my y. It's going to be 1 squared, or is it cubed? Well, it doesn't really matter because it's 1. No, it's just 1. 1 times 2 cubed, because this is xy cubed for the derivative, which is 8 if I want to simplify, but I don't have to. And honestly, you guys, at this point, I'm done because I used labels. Because this f of 1 applies to here, and this f prime of 1 applies to there. So I'm done. Oh, it does say y equals f of x, so I should move this around. So that's going to be y equals f prime of 1 times x minus 1 plus f of 1. There we go. Alright, super easy. Use the tangent line in equation part A to approximate f of 1.1. Okay, so we start out with this thing where y minus f of a equals f prime of a times x minus a, and we know that a equals 1. So at 1.1, that's going to go right here. You get that? Alright, so that's our new thing. So now it's going to be y minus, well, we figured out f of 1 was 2, and this was 8 times 1.1 minus 1. If we were to keep simplifying, we'd have equals 8 times 1.1 minus 1 plus 2 if we move this over to the other side. And then it says determine if the approximation of f of 1.1 is greater or less than the actual value. So is it under versus over estimate? Because remember, under means that we're concave down, and over means that we're concave up, which means they need to look at second derivative. So f double prime of 1, let's see what the equation was. We got to go back and find that. It's right here. Whoa, that looks crazy. Y cubed 1 plus 3x squared y squared. Y cubed plus times 1 plus 3x squared y squared. Okay, so that's y cubed times 1 plus 3x squared y squared. So this is going to be 2 cubed times 1 plus 3 times 1 squared times 2 squared. And honestly, I don't really care what it equals, but I do care if it's positive or negative. And in this case, it's greater than 0. It's positive. Therefore, f is concave up at x equals 1, and the approximation for f of 1.1 is, okay, so we're concave up, and that means we're over, is an overestimate. Done. Alright, so now let's keep going. Same ideas here. Let's look at part C. Find the particular solution with the initial condition f of 1 equals 2. So we know dy dx equals xy cubed. What we have to do is get stuff moved around. So we're going to move the dy and the y together and dx and x together. That'll give us dy over y cubed equals x dx. The right side is going to be easy. I need to fix the left side a little bit before I finish the integration. That's like saying the integral of y to the negative 3 dy equals the integral of x to the first dx. The right side, x squared over 2. No problem. Left side, add 1 to the negative 3, get y to the negative 2 over negative 2 equals this, and we've got to put a plus c in here somewhere. We know that f of 1 equals 2, so I'm going to plug in 1 for x and 2 for y, and let's see what happens. So this left side, to simplify it just a little bit, that would be negative 1/2 times 1 over y squared equals x squared times 1/2 plus c. So negative 1/2 times 1 over y squared is going to be 2 squared. It's going to be 1/2 times 1 squared plus c. So this gives me, oh my goodness, we're going to have negative 1/8 equals 1/2 plus c. So negative 1/8 minus 1/2 equals c. Alright, now do we have to put it all by itself with y? Yes, we do. We have to get y equals f of x. Okay, so that means let's start from here. Actually, let's go to here. So we're going to have negative 1/2 times 1 over y squared equals 1/2 x squared plus c. Okay, I'm going to kind of cheat here. I'm going to do this kind of the shortcut way. So I'm going to multiply both sides by y squared, just like this. And over here, that'll work. And then I'm going to divide by this on both sides, 1/2 x squared plus c. Why? Because I don't have to be particular. You know, I can do this in a really big, complex fraction kind of way, 1/2 x squared plus c. So negative 1/2 over 1/2 x squared plus c equals y squared. So square root this, and that's f of x. And we already solved for c right here. If you want, I could say c1, c1. Boom. Done. Check. Let's finish this. So consider the differentiable function f having a domain of all positive real numbers for which it's known. Okay, so they gave us the derivative. All right, let's go ahead and take it from there. Find the x-coordinate of the critical point. Notice that's kind of interesting. They said the critical point, as if there's only one. And then determine whether the point is a relative max, relative min, or neither. Okay, so I need to start with the equation. Let's take a picture of it here. There we go. Oh, missed it. And clipboard. So we'll paste that in here. It says determine what the critical point is. So we got to figure out either when it's equal to 0 or does not exist. So let's see, when f prime of x equals 0, it's going to say 4 minus x times x to the, times x to the negative 3, which is just like saying over x cubed. And we look at this and we say, well then x equals 4. Now you might be wondering, but wait about, what if x equals 0? X cannot equal 0 because check this out. X has to be greater than 0. So x equals 4 is the critical point for f. At this point, it's asking you to determine if it's a relative min or relative max. Okay, well then let's do a little chart here. X and f prime. So we know at 4 we are 0, but we need to check before that, let's say 3, and after that at 5. If we were to plug in 3, that would give us a positive over a positive, and that would be positive overall. If we were to plug in 5, that would give us a negative on top, but a positive on bottom, so that'd be negative. So then that means f is going up, then coming down while flattening out, so it's going to be a max. So f is a relative max at x equals 4 because f prime changes from positive to negative. Booyah. That was nice and easy. We like that. Find all intervals on the graph for which f is concave down. Okay, concave down translates to the second derivative less than 0. So we got to take the second derivative. If f prime equals 4 minus x over x cubed. Now, you might think that f prime of x would be pretty straightforward quotient rule from here, but I could do some algebra here. Watch this. This will be 4 over x cubed minus x over x cubed, which is really 4x to the negative 3 minus x to the negative 2. Aha! Now take the derivative of that. That's pretty even way simpler. So that's going to give me negative 12 x to the negative 4. Drop the negative 3 times the 4, that's negative 12. Subtract 1 from the negative 3, that gives us the negative 4. Then we got a plus, because this negative 2 is going to drop down, times the other negative, plus 2x to the negative 3. Alright, so now let's go back and simplify that a little bit. So we'd have negative 12 times, oh wait, when is it concave down? Alright, so negative 12 over x to the 4th. And then we got plus 2 over x cubed. We got to figure out when does this change sign. Remember, x cannot equal 0. So that's kind of helpful. And this would be concave down, you know, at times when it would change concavity. So let's do this. Let's set it less than or equal to 0. So negative 12 over x to the 4th plus 2 over x cubed has to be less than 0. Solve it. Move this over. 2 over x cubed is less than 12 over x to the 4th. Multiply both sides by the denominators and we'll get 2x to the 4th. Actually, let's just do this. Multiply both sides by x cubed. Or x to the 4th. That would be even better. X to the 4th. If we multiply both sides by x to the 4th, what that winds up doing for us is over here we have an x, and over here we just have 12. So 2x is less than 12. Alright, solve it even more. X is less than 6. So remember, x has to be greater than 0. So from 0 to 6, this whole thing is less than 0. So f double prime is less than 0 for 0 is less than x is less than 6. Therefore, f is concave down on that interval. Whew, that was good. Now let's say you weren't sure how to figure that out. What you could do is you could set it equal to 0, and what you would find out is that it equaled 0 when x equaled 6. Then you would take a little chart and you'd say x, f double prime, and you'd start at 6, and you would check before and after. And what you would find out is that it's negative here and positive after. So then from 0 to 6, it's negative the whole time, and then positive after that would be positive. So you would look at this interval from 0 to 6. You would have got the same thing. Okay, let's finish this out. Given that f of 1 equals 2, determine the function f. Oh my goodness, that means we got to go back to the very beginning of the equation using this. So I have to take the antiderivative of it. So we did simplify this a little bit. We figured out that it was 4 over x cubed minus 1 over x squared, which was really 4x to the negative 3 minus x to the negative 2. And now what we have to do is take the antiderivative. So that's what we're doing. So take the antiderivative. Well, this constant 4 just kind of stays there, and then we're going to do each of these separate because of the subtraction sign right there, and then we can just add 1 to each power and divide by that number. So that's going to be 4x to the negative 2 over negative 2 minus x to the negative 1 over negative 1 plus c, of course. So y equals this. We know that f of 1 equals 2, so f of x, I should say, f of x equals this. F of 1 equals 2, so that means 2 equals 4 times 1 to the negative 2 over negative 2. Now we got minus minus here, so I'm going to say plus x to the, or not x, we're not using x, we're using 1 for x, plus 1 to the negative 1 plus c. Alright, so simplify this more. 2 equals negative 2 plus 1 plus c. Move these over. We're going to have 2 plus 2 minus 1 equals c. So f of x equals 4x to the negative 2 over negative 2 plus x to the negative 1 plus c. And I'm not even going to bother simplifying that, even though it's pretty easy. It's just 3ac. Done! Done, done, done. Okay, so the biggest thing with differential equations is you're going to have to find the original, which means you're going to have to integrate. But in addition to that, they're going to ask you to do some type of those interpretation things. And remember that the interpretation has to do with, you know, tangents, with concavity, with approximations, all that kind of stuff. Okay, so that's it for this video. A little bit shorter than the other ones. I'm going to stop it here and go ahead and convert it, put it up on YouTube. Hopefully you guys get a chance to watch it.